So here we're going to take a look at some compound radical expressions. Don't let the word compound scare you. Compound simply means that there's more than one letter within the expression. So the first one here you may have seen in Algebra 1. And what ends up happening is you basically have three problems. You have this numerical part, and then you have the x part and the y part. And so what you do is you break this up using a factor tree. I mean, if you're really good, you might know the perfect square root that lives in 108. Most people don't. So you break it down by using the smallest integer that goes into 108 on the left side, and you repeat that process, maintaining the smallest integer on the left side. You know, if you want to do this willy-nilly, you're going to get a weird answer, but if you do it the way I'm describing right now, the answer will always be fairly similar in each problem. So when you take a look at that, what ends up happening is you actually have two pairs, right? Because there's actually two perfect squares, 2 and 3, and then you have your leftover radical 3. So 2 times 3 will come out and make 6. You can write 2 times 3 if you want, or you could just write 6. 2 times 3 is 6, and then you have the radical 3 left over. And believe it or not, you can actually do the letters the same way. So if you want to come over here for the x and write it out as triple x, right? You would have a pair here and a radical there. So you would have an x with an outside and an x on the inside. Remember, the circle means there's one perfect pair, so one x on the inside and one radical x on the, one on the outside, one on the inside. But for the y, you would write it out 6 times, and you would circle pairs. Okay, so you have 3 of them, and you have no radical. There's nothing left over to take the radical, so you would actually have 3 y's on the outside. And that's great. A lot of Algebra 1 teachers will show their kids that, but when you do cubes and fourth roots, it gets a little bit confusing. So the fastest way to do it is actually use division. Remember that the square root has a little 2 here. So if you were to do the x using the division way, you would take the 2, representing the square root, and you would divide it in the fact that you have 3 x's. 2 goes into 3 one time. 1 times 2 is 2, and you have a remainder of 1. This remainder is the quantity that goes in the radical, and the dividend here is the quotient is what goes right there. So for this part, to do it the y way, remember we have a square root. There are 6 y's. So we put a 6 in here for the y's. And then 2 goes into 6 3 times. And notice what happens here. We have a remainder of 0. So that 0 represents the radical, where this represents the quantity on the outside. And we'll use that method for these other ones. So this will be done the same way. You have 3 problems, right? We're going to make a factor tree, because I doubt you know the perfect cube root that lives inside of 108. So smallest integer divisor on the left side, repeat the process. Okay, so what happens here is now instead of looking for pairs, we are looking for triples. And you might have seen the triple over here and understood why I picked these numbers. It is the same problem with different radicals. So this one actually has 2 radicals and 1 perfect cube root. So the 3 will come on the outside, but then the cube root will maintain 2 times 2. So it actually would be a 4 there. So to do the x, I want you to think about this. There are 3 x's. So I can circle just one triple, or I have 1 x on the outside. Again, it sometimes gets confusing, but if you do it the division way, third root is dividing into 3 x's. It goes in there once and has a remainder of 0, and the remainder is how many go in the radical, where this is how many go on the outside. It's very clear, in my opinion, what's going on there. All right, let's take a look at the y part. Again, 3 is going to go into 6. It's going to go in there twice with a remainder of 0. So there's 0 in the radical, and there's 2 on the outside. And if you wanted to do it, again, with the, all of them out like this, it would look like this. You can clearly see it. Some kids like this way, but, imagine instead of me saying y to the 6, imagine I said y to the 64th power. That would be, you'd want to use division. All right, let's take a look at the fourth root. So same problem now with the fourth root. Here we have 2 times 54. And what you notice in this one is that there aren't any at all. There are no quadruplets of the same number. So what do you do when there is no root? The whole thing just goes back in the radical. So this is just going to stay the fourth root of 108, meaning it's not simplified. And you may say, I don't understand. Why would I just leave it like that? Well, think about the square root of 3. Do you do anything with that? How about the square root of 23? Is there anything you can do with those numbers? You cannot. They're reduced as much as they reduce. Just like in this case, the square root of 108, the fourth root of 108 is reduced. So when you look at the x to the third power, again, you can't circle 3 of these. And maybe that makes more sense with division. How many times does 4 go into 3? Now watch how much sense this makes with division. 4 goes into 3 0 times. 4 times 0 is 0. It has a remainder of 3. So remember, the remainder is how many go inside of the radical. That's why I really like the division way, because it really shows you what's going on there. So for the 6, if I take 4 and divide it into the fact that there are 6 of them, it'll go in there 1 time with a remainder of 2, right? 2 is the remainder, 1 is what goes outside. So I would just have a y on the outside and then 2 y's on the inside. If you want to see the visual way where you draw out all 6 y's, right? There are 4 here and a radical of 2. So same problem 3 times. Hopefully that'll really explain to you how to group together those radicals. Now let's take a look at what happens when we use that in a multiplication or division problem. And I know that these problems look like they're like monumentally different. And they are, this is one of those times in math where the problems look difficult, but they're actually fairly simple. So the way this works is, notice that here they have a 1/3 and a cube root. That actually means that they have the same radical. So remember, the rule from earlier in this lesson is if you have the same exponent, in this case the third root, then you can combine the bases. So the way I combine the bases is I do 4 times negative 16, right? That would be negative 64. And then here, when I have the same base of x, I would combine the exponents by adding. So 12 plus 6 is 22. And then for the y, I have the same base here, this y and this y. I would combine those exponents by adding, giving me 13. All right, so now if you look at that problem, it looks scary, just literally 30 seconds ago. I basically have a problem that's identical to these problems, right? It's like identical to number 2 here. So what I'm going to do is I'm going to break this down, and you notice there's a negative, so we're going to talk about that in a minute. But I'm going to break this down the exact same way I did the other one. This is divisible by 2. And you might know that there's an 8 in here, so you might be able to do this a different way using the just factor way. But I like using a factor tree. It just really helps a lot of students with seeing the visual of what we're trying to do. All right, we're looking for 3 of them. Okay, so check this out. The cube root of 64 is just 4, because 2 times 2 is 4. So the rule of thumb I like to do on a problem like this is think to yourself before you start, you might want to enter that into the calculator and see if you get a decimal. If you get a decimal, you have to make out all these trees. But if we were to type if we were to type in the cube root of 64, it would just tell us the answer is 4. Okay, so the cube root of 64 is 4. But when taking a cube root of a negative, you actually take the negative out first. And the reason is that negative could be negative, negative, negative. So when you take the cube root of this, there's a negative that comes out. So this answer will start with a negative, and then it will have the 4 from this group of 2 and that group of 2. So we start with negative 4. And that takes care of the negative. We don't have to worry about it anymore. So here you can really see why someone would not want to write out 22 x's. I just want to divide 3 into 22, right? 3 goes into 22 7 times with a remainder of 1. So I'm going to have in my radical expression down here, when I write out my cube root, okay, I'm going to have 7 x's out here. and then a remainder of 1x in here. The negative was already taken care of. Same thing for the y's. It might be reasonable to write out 10y's, but it sure is a whole lot easier to just divide it by 3. It goes in there 3 times with a remainder of 1. So I'm going to have 1y here and 3y's outside. So division, okay, so remember that was a cube root. You take a negative out of a cube root and place a negative there. Division's the same way, and most people won't make you divide and have to rationalize. If you see that, you think rationalization. This is going to divide evenly, and so what we do is we just change the square root, right? The square root in this 1/2, we just change this to one huge square root problem. And please make sure you try to divide it before you actually reduce it, because I know that this looks like a radicalization problem from just a couple minutes ago, but the reality is that you don't have to rationalize something that doesn't have a denominator left over. So that's an important thing to remember. So let's see what happens when we actually try to divide this. And remember, the rule for division is this. You divide integers by simply dividing this. So this comes out to -2. And you divide the bases by subtracting the exponents. That rule is from Algebra 1, maybe even pre-algebra, depending on when you learned it. So that x right there is squared, and this x is to the 14th, so 14 minus 2 would be x to the 12th. Okay, and then the y's, you have 9 minus 3, so 9 minus 3 would be 6. And if you ever need an explanation for that, it's very similar to the circling method. If I were to write out 9y's, right, y, and then I write out 3y's here, I would cross out 3 of them, leaving me with 6 of them. So now I'm going to break that down using a root. The first thing here, the number doesn't break down at all. So here we had this huge tree we had to do. Here we don't have a tree at all. So when taking the square root of a negative, so if you square root a negative as a cube root, you actually remove an I. And that's just an introduction to something that we're going to talk a lot more about when we get to the quadratic chapter. I just want you to realize what happens is that square root is I, standing for imaginary. Don't worry, we'll talk more about that in the next unit. For now, I just want you to know that radicals of square roots of negatives are i's, cube roots of negatives are negatives. All right, so to do the 12, I'm going to take 2, because it's a square root. Remember, there's a little 2 right here, and I'm going to divide it into 12. That's very easy math. That goes in there 6 times with a remainder of 0. 0 being the radical, 6 being what is outside here, so x to the 6th. And then the last one is 2 for the square root. There's a little 2 right there going into 6. It'll go in there 3 times, and again with no remainder, so nothing on the inside. So we have y to the 6th. So you end up getting this answer of x to the 6th, y to the, sorry, not 6, to the 3rd. Okay, and then the square root of 2. The square root is the only thing it didn't break down. So remember, the key here is don't freak out over the fact that they look like they're really big problems, and understand that those problems can be combined using the same radical by just multiplying and adding the exponents or dividing and subtracting the exponents. Then you break it down just like you did these problems.